everyone, and welcome back to another Tar Talks episode. This episode, I promise, I'm going to be entirely silent because I cannot get myself to do a full script on this.
You'll start
This-
crying.
I will fully. This entire
It
thing was.
fails at the subject.
I have never failed. Guys, I am a maths AHL student, okay? I
It fails.
never failed.
Okay.
I must have some ounce of mathematical understanding to take like complicated IB mathematics, okay? So I know I'm not bad at math. I'm just bad at AHL.
You just leave it, never mind.
So, Reena, what is this episode about?
So it's about imaginary numbers. So I know you don't know what it is.
I obviously know what imaginary numbers are, but
Sure.
for our audience,
It's fine. It's fine.
for our audience, what are imaginary
Look,
numbers?
I knew it. You couldn't explain it. So
I will explain it now. Imaginary numbers is basically the square root of -1. So for those of you who don't know what a square root is, I'm just gonna quickly give you an example. 2 into 2 is 4. So the square of 2 is 4. Right?
Oh, Prisha, you did maths.
But the square root of 4 is 2. Does that make sense to you?
No.
Okay, guys. But what's so surprising or so absurd about imaginary numbers, or the reason they're known as imaginary, is how could the square root of anything be a negative number? Like, imagine this entire thing. If you multiply -1 into -1, you get +1, not -1. Meaning that no square root or no number squared by itself can ever, no number multiplied by itself can ever give you a negative number, right?
So, but then still, they turned out to be indispensable in physics, especially in the development in quantum mechanics, electrical engineering, and signal processing.
So I'm going to be honest, I'm a biochemistry student. I have absolutely no comments on that. Mine is like quantum mechanics because I know about that from Big Bang Theory.
That's sad. You learn from a series which is meant for comedy.
Right? Not physics, man. That's not my thing.
So, in quantum mechanics, the Schrödinger equation, which governs the behavior of particles at the atomic level, it inherently uses imaginary numbers.
So I do actually know a lot about Erwin Schrödinger, and I do know about Erwin Schrödinger's contributions to quantum mechanics and quantum physics as an entire field. And through this Schrödinger's equation, he is able to completely explain how each particle moves at a very subatomic level. This equation makes use of imaginary numbers, meaning they're not entirely useless.
These numbers aren't just mathematical tricks. They describe the probability amplitudes, which determine when the particles are likely to be found.
So this again relates back to Schrödinger's equation.
Yes.
As you know, you can understand. See, I know all of this. This relates back to Schrödinger's equation. Well, whatever. I like Erwin Schrödinger. Erwin Schrödinger is my favorite scientist, actually. So what this, basically allows you to understand is with the iota or the imaginary number present over there, the amplitude of the wave that is being found actually helps you understand where the subatomic particles could be found at that present moment in time.
So now let's move to the story of imaginary numbers. So have you ever heard about the story of the birth of mathematics and the cubic equation conundrum?
Very vaguely, tell us about it.
So mathematics began as a practical tool for commerce, land measurement, and astronomy. However, during the Renaissance, mathematicians encountered the cubic equation, a problem that defied solutions using the existing mathematical framework. The challenge led to the conceptualization of imaginary numbers.
So the secret solution to the cubic equation is a completely interesting story within itself. In the 16th century, a professor at the University of Bologna discovered a method to solve the depressed cubic equations. Trust me when I say the words depressed cubic equations sound just as odd to me as they do to you. But I do know what they are. I researched upon this. ChatGPT upon this. A normal cubic equation has your x cubed term, your x squared term, your x term, and your constant term, right? But then a depressed cubic equation does not have your x squared term. It has your x cubed term, it has an x term, and it has a constant. But it does not have, x squared term. And like any other normal cubic equation, this can also be equated to 0. And what this professor basically did was find a way to solve this. So he kept his method a secret until his deathbed, when he revealed it to his student, Antonio Fior. Fior, in turn, disclosed it to Fontana Tartaglia, sparkling a mathematical rivalry.
So Tartaglia developed an algorithm to solve the depressed cubic equation and presented it as a poem to protect his discovery. Girolamo Cardano, as much persuasion, learned Tartaglia's method and expanded upon it to solve generic cubic equation despite promising secrecy.
And what Cardano's work basically led to is the equations in solving the roots of negative numbers, in which he initially dismisses entire thing as useless, right? Because again, the roots of negative numbers made no sense to people back then. And that is when we had Rafael Bombelli come in, who's an Italian engineer who embraced these square roots and developed a method to solve cubic equations involving them. This is the first time that we can identify the introduction of imaginary numbers.
So, imaginary numbers, once seen as abstract, being fundamental in quantum mechanics, the Schrödinger equation, central to quantum physics, including imaginary numbers, indicating their essential role in describing the behavior of quantum particles.
And for everyone like me, who is so love to claim that imaginary numbers are not real numbers and should not exist, quantum mechanics and quantum physics is something very real. And if an abstract concept can be used to describe something like that, that is when I think we can actually quantify it as something worthwhile and something useful.
So, we created imaginary numbers to solve problems that seemed unsolvable, but it turns out that the universe seems to run on them.
Right? Which is exactly why I'm still in AHL and I'm still learning mathematics, because it does explain a lot about the universe. So those were the imaginary numbers on to Hard Talks. Thank you so much for joining us today. And we hope this episode rekindled some ounce of interest in all of you for mathematics.